Hello friends. In the last lecture, I promised that I will discuss about the inverse Laplace theorem in the coming lecture. But before that, I think we need to see some more examples and some theorems. Those are important before going to the inverse Laplace theorem. So now we covered this today, and hopefully, if we cover everything, and then we will discuss about the inverse Laplace theorem in the next lecture. So suppose Laplace transform of capital Ft is given by Fs, small fs. So this is given. Now we want to find the Laplace transform of t to the power n capital Ft. So we want to find this. So you are multiplying your given Ft by t to the power n. So what would be the answer then? Then simply the answer will be minus 1 to the power n. So this n coming from here, and nth time derivative of your small fs means Laplace transform of this. So this is the formula. We first prove and then see some examples. So suppose by the definition of Laplace transform and our notation, we already know this thing because this is the Laplace transform of capital Ft. So which is equal to 0 to infinity into a minus st Ft dt. Now I already in some previous lecture I told you the Leibniz rule for differentiating under the integral sign. So if we differentiate this f, then dfds, that is f dash s, can be written as dds of this term. So this is our f, small f. So now this using this Leibniz rule of differentiability, this dds come inside, this thing come inside as a partial derivative del s of this e to the power minus st ft dt. Now ft, there is a nothing in this term. In ft there is no term involving s. This term is involving s. So we need to differentiate this. So if we partial derivative this, then ft works as a constant, and if we differentiate e to the power minus st, we get minus t e to the power minus st. So this term we get. Now this this can be written as e to the power minus st. So I just take this t and ft together. So this becomes t ft dt and minus e to the power minus st. So now if this minus is taken out of the integration, now you get that this is the Laplace transform of tft. So we get minus Laplace transform of tft. So this is the minus Laplace transform of tft. Thus, Laplace transform of tft can be written as, if we take this negative sign here, then we get minus df ds, that is minus f dash s. So which prove our theorem for n equal to 1. So we prove the theorem for n equal to 1. And now we use the mathematical induction. So how will you do? So now use the mathematical induction. So what is our induction hypothesis? So assume that the theorem is true for n equal to any arbitrary k, where k is equal to greater or equal to 1. So therefore 0 to infinity e to the power minus st t to the power k ft dt equal to minus 1 whole to the power k fk ds. So this is our assumption. This is our assumption. So if this is our assumption, then now we try to prove the statement for k equal to 1. Now we prove for k equal to 1. So for that, we want to differentiate with respect to s. So if we differentiate this whole thing with respect to s, what we will get? So here minus 1 to the power k will be as it is in the right hand side. And this differentiation of this becomes f, differentiation of fks will become f to the power k plus 1s. So this thing is easy. Now differentiate this left hand side. So dds of 0 to infinity e to the power minus st t to the power k ft dt. Now again use the Leibniz rule. So this dds comes as a del s, and if we differentiate it, then if we differentiate this e to the minus st, it becomes minus t e to the minus st, and tk ft dt will be as it is. So we just multiply this t here and take this negative sign to here. So it becomes right hand side becomes by, if you multiply this negative both side by minus, so this will be become positive and this becomes a k plus 1. So minus 1 to the power k plus 1, if k plus 1 is the right hand side, and left hand side this t and t to the power k becomes t to the power k plus 1 ft dt. So from this, what can I say? So this left hand side is this simply the Laplace transform of t to the power k ft. So this left hand side is the t to the power k ft, and right hand side become minus 1 k plus 1 f to the power k plus 1 s. Therefore, the statement is true for n equal to k plus 1. So by induction, we complete the proof. So solving many equation problems, we this formula will help us. So see some example. So find Laplace transform of t sin at. So you know the Laplace transform of sin at equal to a divided by a square plus a square. So what would be the Laplace transform of t sin at? So Laplace transform of t sin at will be, so you have t to the power 1. So you have a power t to the power 1. So what will be there? Then if you need to differentiate this term once because it has a power 1. So you have to differentiate this term once. So this is minus dds a by a square plus a square. So differentiation of this is given by this. So we already discussed the Laplace transforms of this using the definition in our previous lectures, where we studied those things, the elementary things. So you can compare this result with that result. So this is much easier. Similar for another, see another example, the Laplace transform of t square cos 80. So you know the Laplace transform of cos 80 is equal to s by s square plus s square. And now you want to take the Laplace transform of t square cos 80. So Laplace transform of t square cos 80. So you have power 2. Look, you have power 2. So you have minus 1 square and you need to differentiate twice. So there is a mistake. This would be, you need to differentiate d2 ds2. So you need to differentiate this is twice, s by a square plus a square, and this will give you a simple calculation. You can find this value. So in this way, we can use the property by multiplication by t or power of t. Next, another theorem, and this is division by t. So suppose Laplace transform of capital F t is given by small fs, then Laplace transform of ft by t is equal to s to infinity fu du, provided this Laplace transform of ft by t tends to 0 as s tends to infinity. So this condition we need, and then this condition can happen. So now try to prove. So simplicity, we assume this ft by t as gt. Assume ft by t as gt. Then what we get? Then ft equal to tgt. So you just take this t here. So this becomes ft equal to tgt. Now take Laplace transform of this both sides. So Laplace transform of ft equal to Laplace transform of tgt. Now use the previous theorem, the multiplication by t. So you know that here t to the power 1. So you need to differentiate the Laplace transform of this gt once with minus sign because you have minus 1 to the power 1. So for that, this is minus 1 to the power 1, you have minus. So this is minus dds of Laplace transform gt, and Laplace transform gt we denote by small g. So this is equal to minus dgds. Now integrate both sides. Now you need to integrate both sides. So integrate both sides from what is the range? From range s equal to s to s equal to infinity. So we take this integration. So Laplace transform s to infinity, Laplace transform of L of ft dt. So then we get this Laplace transform of ft dt. Laplace transform of ft is denoted by some f of u. I just use the definition here. And then if you the integration and differentiation are inverse to each other, so you by fundamental theorem of calculus, we can write this is g of s minus g of infinity. Actually, you write this is g infinity minus gs, and this minus will there like minus, but if you multiply by this minus, so you get gs first and minus g. Now this g infinity is equal to 0 by our assumption. Why? Because we have this assumption. So this is our g. This is our g. So g of infinity is equal to 0 because this is given. So this assumption we get this term is 0. So this becomes L of gs is equal to L of ft by t by definition of g. And this becomes 0. So this is Laplace transform gt by t. So therefore, sorry, this should not be gt. This should be f. This should be f. So Laplace transform of ft d by t is equal to s to infinity f to d. So I think I should correct this. Now we try to solve a very interesting problem, and this is an improper integral. Next example, see the next example. So that 0 to infinity sine t by t dt equal to pi by t. So using Laplace transform, we can solve this improper integral. This integral is not that easy to solve in general, but Laplace transform help us. So how? So suppose ft equal to sine t. So if you have ft equal to sine t, then this small fs, which is the Laplace transform of ft, this is equal to Laplace transform sine t equal to 1 by s square plus 1. So this is easy. Now look. So therefore, integration s to infinity 1 by e square d, that is equal to Laplace transform sine t by t, which is equal to 0 to infinity e to the power sp sine p by p dt. So p is value. So this is by definition. So this is the definition of Laplace transform, simply sine t by t. So here this is our f function. We are multiplying by e to the power minus. This is by definition, and already we proved that this integration. So this is your fs. So you are taking the integration. So whenever you taking integration, the previous theorem, you know from this result Laplace transform ft by t is equal to integration s to infinity f u d. So using this, you have Laplace transform of sine t by t is equal to s to infinity 1 by u square plus 1. Now taking this s tends to 0. So if you taking s tends to 0, so here this become s equal to 0 to infinity 1 by u square plus 1 du. And here you put s equal to 0. So if you put s equal to 0, then e to the power 0 is 1. So you have 0 to infinity sine p by p dt. And now what is the integration of this? This is tan inverse u. So we put tan inverse u 0 to infinity. And at infinity, tan inverse becomes a pi by 2 and 0 is 0. So this becomes pi by 2. And this is the integration 0 to infinity sine p by 2. So in this way, we can solve this type of complicated integrations, improper integrations. Now we state two more important results, but we don't use very much. For the this is not very much important for the BTech student, I think. Um, if anyone has any query and they want to the proof for this theorems, they can message me in the comment box and I can try to make a video for this theorems also. So I just state this theorem. So what first is the initial value problem. What is initial value problem? So suppose you have a function ft and t tends to 0. So 0 is the initial value. Then this initial value problem can be written as final value problem, that is limit s tends to infinity s f. So this is quite an interesting uh, observation, that if you are given a function And if you're tending the t value is tending to 0, that is equal to s. This is the Laplace transform of this function. So this will get limit s tends to infinity sf. And similarly, a final value problem. So here limit t tends to infinity ft dt is equal to limit s tends to 0 sf. So here this is a final value t tends to infinity, and here you are getting limit s tends to 0. So this is tending to initial value of s. So there is very beautiful, these two are relations, but I am just state this result. Now also we try some example using try to solve improper integrals using Laplace transform. Find 0 to infinity t to the power minus 2t cos t d. So simply look that this can be written as the Laplace transform of t cos t. So Laplace transform of t cos t. So we already proved that this is equal to minus. Here since t to the power 1 here, we have minus 1 to the power 1, that dds one time derivative of Laplace transform of cos t. And Laplace transform of cos t is s by s square plus 1. If you differentiate, we will get this one. So this is the general for any s. Now here given it is s equal to 2. So put simply s equal to 2, and you get this result 3 by 25. So there is another very beautiful application of the Laplace transformation to solving improper integral. So there is another easy exercise for that. Solve this integration 0 to infinity e to the power minus t minus e to the power minus 3t by t dt. You can solve this problem by using the division by t property, and you can check that answer will be log 3. So this all for today. Hopefully next day we can start the inverse.